So in this session we're going to study Sigma protocols and zero knowledge, just to get a bearing on things. Who here has studied zero knowledge before? Excellent. That's a vast majority. What about proofs of knowledge? Okay, so we're less there. Zero knowledge, in general, we have a prover and a verifier, some language L, and the prover wishes, and they have some comment statement X, and the prover wishes to prove that X is in the language without revealing anything else but that fact. And as in any proof system, we have the following properties. Completeness means that a correct statement can be proved within this proof system. So when P and V are honest, the prover and verifier are honest, and they interact on a statement that's in the language, then the verifier will accept. Soundness means that you cannot prove incorrect statements in your proof system, and that means that for any X that's not in the language, the verifier will accept after interacting with any arbitrary cheating prover with at most negligible probability. So this deviates significantly from a classic written proof system where we're used to reading a proof written on paper. It's a soundness means that you're never convinced of anything that's incorrect, and here you can be convinced with negligible probability. In addition, it's an interactive proof, so it's not something written on paper. It's really me up here convincing you that it's correct, and but obviously based on mathematical rigor and not my amazing charisma. Beyond the that was funny. Beyond the regular notion of soundness for proof systems, there's also something called an argument system, which means there's only computational soundness, and that means that soundness is only guaranteed when the prover is bound to be polynomial time. So if the prover is all-powerful, then it can convince the verifier of an incorrect statement. In crypto, you could argue that arguments are essentially what you need, and proofs are really an overkill, because why should I care if the prover is all-powerful? However, in some settings we would like to consider an asymmetric setting where the one party may be more powerful than the other, and then this way the weaker party has guarantees that, that it's not going to be cheated at all. In addition, it turns out that there are a number of transformations and that are easier if you have a proof rather than an argument. When using it as a sub-protocol inside something else, it sometimes may be easier if you have a proof and not an argument, because it's an information theoretic concept, and so on and so forth. But in general, in cryptographic settings, computational soundness is enough. What does zero knowledge say? Zero knowledge says that we have a simulator. So this is similar to yesterday, although this predates it, that is able to generate a transcript that looks close to a real proof execution. And here, close to is exactly the same as yesterday. If it's computationally indistinguishable, then it's a computational zero knowledge proof. If it's statistically close, then it's statistical zero knowledge. And if it's exactly the same, then it's perfect zero knowledge. So that's exactly the same as yesterday. Note that in general, we need this to hold even if the verifier is malicious. Now, one might think, well, what can a malicious verifier do? Well, in general, the verifier can just make our life very difficult by doing stupid things like sometimes aborting and not continuing. If it has to commit and decommit later on, for example, with some probability it will decommit and with some probability it won't, and this may depend on the messages it gets, and it seems like a very benign sort of thing to do, but that's actually what makes life, our life hard when we're trying to prove that we're generating a transcript which is the same. What's a proof of knowledge? And this is less known, and it's I'm not going to spend too long on it, but it's actually quite a difficult notion. How can I say that a machine knows something? How can I know the student knows something? I can try and give them a test. It doesn't necessarily mean that much for a machine. It's even worse. How do I know that a machine knows something? I want now for the prover to convince the verifier not that X is in the language, but that the prover knows a witness to the fact that X is in the language. Now, sometimes the fact that X is in the language is just something which is completely trivial. For example, if I'm proving that I know the discrete log of some value. So I have a group and I have a random value in the group, and I have a base, I have a generator for the group G, and I want to prove that I know some value x, so that G to the x equals this random value H. There's always, we know that there is always such an x. So the fact that H has a discrete log is trivial. It's always in the language. It's a trivial language. But now I want the prover to convince the verifier that he actually knows a witness to that fact. He actually knows the value x, or the G to the x equals H. So how do we formalize this concept of knowing something? This is difficult. Like I said, we want it to be zero knowledge. The way it's written is as follows, and I'll say the technical meaning and then I'll discuss it more. We want there to exist something called an extractor that manages to obtain the witness by interacting with the prover. Bit more exactly, so we have some cheating prover that, well, let's make it easy to start with. Let's say the prover always convinces the verifier. Then we want to construct we want an extractor that will always obtain a witness from that prover. What does it mean to obtain a witness from the prover? It means, obviously, it can't be trivial to do because the verifier isn't supposed to learn anything. So the verifier is not supposed to learn anything, but the extractor is supposed to get the witness. It has to be zero knowledge and somehow that you can actually obtain the witness. These things obviously contradict. So the extractor is given extra power. It can interact with the prover, rewind it, run it many times, change things, play around with it, whereas a real verifier just has an online interaction with the prover. So how do we formalize again this notion of knowing something? The idea is that if I can be used as an algorithm to output the witness, then it means that I know the witness. So how am I using an algorithm to output the witness? Again, we have this extractor which will interact with the prover, we'll send it a message, send it a different message, rewind it, try again, and eventually we'll obtain a witness. That means that the prover must actually have known that witness, because the extractor itself doesn't know anything. Especially if it's a hard language, the extractor doesn't know anything and somehow it managed to get the witness, it must be that it came from inside the prover. And that's the idea of a proof of knowledge. Knowledge is not something in the air, something philosophical, but it's actually being able to output the string. But it doesn't mean that I output the string because I'm a machine who's a prover. I don't ever output the string, but it means that somebody can use me as a black box in order to obtain the information. Now that's if the prover always succeeds in proving. But what happens if we have a prover that succeeds in convincing the verifier with probably only 1/2, or only 1/4, or 1,000th? Then what we want to guarantee is that the extractor will obtain a witness from that prover with approximately the same probability that the prover convinces a real verifier. And that's what we want, and it turns out this is very, very useful. In fact, not just useful, it's actually crucial in secure computation settings. So yesterday Benny discussed GMW, and he talked about you have to commit to your input in the beginning. In fact, actually what you have to do is you have to run a zero knowledge proof of knowledge that you know your input, so that the simulator in the secure computation setting can extract that input and send it to the trusted party. Remember that in the ideal model, the simulator has to send the party's inputs to the trusted party. How does the adversary's inputs, how does it get it? Essentially it gets it in the GMW type constructions from a proof of knowledge. An equivalent way of doing it, which is using the notation of secure computation, is that we define a function where the inputs, both parties have common input x, but the prover also has an input w, and the output, the prover doesn't get anything, doesn't need to get any output, and the verifier just simply gets the output of the relation on that pair, either 1 or 0. So if it's 1, the verifier actually knows that the prover knows a witness. Now, if you think about this in the ideal model, it becomes very, very clear. The only way that the trusted party is going to send 1, meaning that the relation was fulfilled, to the verifier is if the prover actually sent the witness to the trusted party. The trusted party can verify itself whether or not this witness is a valid witness. So if you think about it in this sense, it's a very, very clean way of talking about a proof of knowledge. And in fact, it can be proved that any zero-knowledge proof of knowledge, as classically defined, meets this functionality. You may think that's a trivial, straightforward sort of proof. I mean, what's the difference? In fact, it's quite involved. But if you want to think about this, this is the best way to do it. You have an ideal model where the trusted party will verify that the prover actually knows the witness. Okay, so zero knowledge is an amazing concept. Everything can be proven in zero knowledge. It's central to fundamental feasibility results like GMW, we talked about that. But can it be efficient? In fact, many people, when trying to design an efficient protocols, steer away from zero knowledge. Because zero knowledge seems like something that's inherently inefficient, especially if what you've studied is, okay, so I studied one or two protocols in perfect zero knowledge, which seemed reasonably efficient, but not that efficient because I had to repeat them to get low soundness. I had to repeat them many, many times. Or I studied general, I learned the general proof that everything in MP can be proven in zero knowledge, and then I had to do a carp reduction from my language to 3 coloring with Hamiltonicity, and that's obviously something which is horrific if you actually wanted to do it in real life. And so therefore, zero knowledge to some extent gets a bad name as being something which is an amazing concept, great, something you can really tell, you can actually tell other people you're doing. This is like in your research, this is something which people can sort of understand, but not something which is actually really very useful in practice, and sometimes you try and avoid zero knowledge at all costs, and this is actually not true. In fact, zero knowledge can sometimes be the most efficient way to achieve something within a secure protocol. And I'll just mention, very often GMW again is considered a general feasibility result which doesn't have that much impact on practice, but it's not true, because quite often when we construct highly efficient protocols, we follow the same paradigm as GMW, which is implicitly have everybody commit to their inputs and then have them prove that what they're doing is correct. But rather than do this by a general carp reduction without looking at the insides of what's going on, we set up our protocol and design our protocol so that it's tailored to an efficient proof that everything is done correctly. And if you're using Sigma protocols, this is a very, very useful and clean tool which enables you to do that. So there are many general tools for Sigma protocols. Once I design a Sigma protocol, I can get immediate cheap transformations to all different things, and we'll see that. And there are also many interesting languages that can be proven with a Sigma protocol. So let's start with an example. An example is the famous Schnorr's proof of the discrete log of a value. So we have a group G of order Q, and I have a generator G. And P and V both have some input H, which is in the group. But P also has a witness, so that G to the power of W equals H. So the prover knows the discrete log of H relative to G, he knows this W, and the prover wants to convince the verifier that, that he knows this W. Often this is considered like as an identification protocol. I want to prove who I am to log into a server, so the server will have H, and I will know W, and then I'll prove that I know W, and since nobody else can prove that, this verifies my identity. But as we'll see later on, this proof actually has many applications which are similar to things like proving that I know an encrypted value, proving that I know the committed value, proving that a committed value equals something specific, and these are much, much closer to what we think about in secure computation. So I'm interested in talking about zero knowledge and looking at zero knowledge not as for identification protocols or for other things, but in the context of secure computation. So how does P do this? First, P chooses a random R and sends G to the power of R to the verifier V. That's A. In our Sigma protocols, we'll always denote the messages as being A, E, and Z. The verifier will send its challenge, which is the random E of length T, assuming that Q is greater than 2 to the power of T. So this is some value smaller than Q. And the prover will now send Z, which equals R plus EW mod Q. What you need to think about is that the verifier, in terms of zero knowledge, the verifier sees some value A, and afterwards sees R plus EW. And the point is that since essentially R remains quite hidden, even given A, and I say quite hidden because it's not all hidden, because it's just a discrete log, it's not a DDH or anything, but R remains quite hidden given H, that R is enough to hide W. It's not a very strong argument, but we'll see formally how I can say it later on. Now what V will do is simply check that G to the Z actually equals A times H to the E, and be convinced if that's the case. Let's see why completeness holds and then try to explain things more. So let's look at this check by V. V computes G to the power of Z, but Z equals R plus EW. Remember, we're talking about completeness, so everything is done honestly. So Z equals R plus EW, so that's equal to G to the R plus EW, which is G to the R times G to the EW, or I can write it the other way around, G to the R times GW to the E, but H is G to the W. So that means I get that and G to the R is A, so it's A times H to the E, and therefore the verifier accepts. So this is something which always can convince you. And if you thought about E as being a single bit, just one bit, a 0 or 1, then basically what you would have is a simple cut and choose here. Over here you have P sending some value G to the R, and then the V would send either 0 or 1. If it sent a 0, the prover is supposed to reply with R, because 0 times W would be 0. And this would be basically the prover saying, yes, I know the R, I know the discrete log of the value A that I sent you. So A equals G to the R, and the verifier saying, with probability 1/2, I'm going to check that you actually know R. And that's what he does. And with probability 1/2, it's going to be 1, and if it's 1, the prover is supposed to send R plus W. And then the verifier is saying, okay, assuming that you actually know R, if you manage to send me R plus W, then you must know W. So that's the idea. If I know that you know R, and you manage to send me R plus W, and I can check that G to the Z is A times H, that means, A is G to the R and H is G to the W. So it means you must know R plus W. How can I be sure that you actually know R? Well, that's the case that I send you 0. If I send you the 0 bit, then you must know R. So when you think about zero knowledge for this sort of thing, very often you prove this to be zero knowledge by looking at the 0-1 case. And the 0-1 case, it's easy to see this is zero knowledge because all I need to do is guess the bit that the verifier is going to send. And if I know that it's a 0, then I'll just compute G to the R. I'll take R and compute G to the R, and they'll answer R, and that's fine. And if it's going to be 1, then what I'll do is I'll send A, which equals A divided by... Sorry, I'll compute... we'll see in a second, actually. It's on the next slide. But the problem is that if I'm looking at E to be a single bit, this is going to be inherently inefficient. So usually when we study zero knowledge, we think we say, okay, so this is the way Schnorr talked about it, but this is not the right way to look at it because this is clearly not going to be zero knowledge because I can't guess a long string from the verifier, and therefore we just use a single bit. As soon as you've done that, you've basically destroyed the whole beauty behind the Sigma protocol because instead of being something with how many exponentiations? 1, 2, 3 exponentiations. It's going to now be something which has, I have to repeat 40 or 80 times, and it's going to be much, much more expensive. So that's the one side of zero knowledge, but we'll talk about how to solve that problem later on. For it to be zero knowledge, essentially I'll need to know what the value E is ahead of time, because we'll see in a moment, if I don't know that, there's no way that I'll be able to answer correctly. In general, if you think about general zero-knowledge proofs, that's the way they work. They work by you knowing the verifier challenge ahead of time, and the same thing will be here. If the verifier challenge is very short, then I can know ahead of time just by guessing it. And if I'm wrong, I try again and again and again until I'm right. Remember that as a simulator, I can run the verifier many times. If it's very long, it's going to take me 2 to the power of t time, and I want t to be large. I want t to be at least 40 or 80. I'm just not going to have time to do that. So why is it a proof of knowledge? And this will also answer to a certain extent why it's not zero knowledge. I want to argue that if the prover is able to complete the proof with any reasonable probability, in fact, with probability greater than 1 over 2 to the t, then the prover actually must know the value, the discrete log. Okay, so over here you have the sketch of the proof so you can remember how it looks. Let's assume that the prover can answer even just 2 queries for the same first message. Okay, if the prover can answer only 1 query, then I'm not concerned. Why am I not concerned? The chances of the verifier accepting are almost 0. It's just 2 to the power of minus t. So if the prover sends any A and can only answer for one E, then that's going to be the negligible probability that the cheating prover convinces the verifier. It's just 2 to the power of minus t. So, and what I'm going to show you now is that as soon as the prover can answer just 2 queries for any given A, it must mean that it knows the value the value W, sorry. So we're assuming the P can answer 2 queries E and E prime for the same A. That means that it can send some Z and Z prime that are correct answers. Okay, so what does that mean? It means that in the first query E, we'd have G to the Z equals A times H to the E. That's a correct answer. The correct answer is an answer that convinces the verifier. Note that I'm not looking at what the prover should send here because I have no idea what the prover is going to do. This is an arbitrary cheating prover. But an accepting message is one that would cause the verifier to accept, which is over here. So does the verifier computes G to the Z and A times H to the E and compares them. So we have the G to the Z is A times H to the E, but we also have the G times Z, G to the power of Z prime equals A times H to the power of E prime. It's the same A in both because that's what we mentioned, that the idea is that the prover can can answer 2 queries relative to the same A. Okay, so what does that mean? Noting that I have the same A on both sides, that means basically that A equals G to the Z times H to the minus E, but A is also equals to G to the Z prime times H to the minus E prime. In other words, G to the Z times H to the minus E equals G to the Z prime times H to the minus E prime. Okay, because both of these values equal A. Okay, so let's continue. That means that G to the Z minus Z prime equals H to the power of E minus E prime, just by transferring sides. But that means that H equals G to the power of Z minus Z prime divided by E minus E prime. Now, E minus E prime does not equal 0. Why not? Because we said it can answer 2 different queries. Now, furthermore, what's important is that Z, Z prime, E and E prime are all public values. You know, they're all values that are sent in the transcripts. Right? That's exactly A, E, Z, and after I have A, E prime, and Z prime. All I have to do now is compute Z minus Z prime divided by E minus E prime mod Q, because we're in the exponent, and I get that that's the discrete log. So the discrete log of H is actually Z minus Z prime divided by E minus E prime mod Q. And I can easily compute that efficiently. So that's my extractor. If the prover can answer 2 different queries, I'm able to obtain the correct value. This also says why it's not zero knowledge trivially, because if I have to generate an A and I'm unable to guess what the next value is, I'm only ever going to be able to answer at most 1 value for 1 E from the verifier. If I don't know the verified query ahead of time, because of this, I can only answer 1. And I'm not going to be able to simulate this way. So the conclusion is that the prover can convince the prover with probability, can convince the verifier with probability greater than 1 over 2 to the t, then it must actually know the witness. So what about zero knowledge? As I said, it seems that it's not zero knowledge. I only said that it seems. I can tell you it's definitely not black box zero knowledge because there's no black box zero knowledge with 3 rounds, but I can't prove to you that it's not zero knowledge. At least I can't. I don't know if anybody can today. I think they can't. But it is what's called honest verifier zero knowledge. What's honest verifier zero knowledge? This is like semi-honest adversaries. This is the nice guy. The verifier has it's a random tape, and on that random tape there's a random string, and that's what it uses to send E. So if I'm simulating for that verifier, I can just look at what the query is going to be, and that query is not going to depend on A, it's not going to change, it's just going to be E. And now I'll show you that if I know E ahead of time, if I know the query of the verifier ahead of time, then it's easy for me to simulate. Why is that? So all I'm going to do is choose a random Z. Well, looking at the E on the random tape of the verifier or choosing a random E is the same distribution. So I can choose a random Z and E, and then I compute A to be G to the Z times H to the minus E. It looks very, very strange, but note that A, E, and Z have the following property. Firstly, they have E's has the same distribution. A is going to just be a random value in the group, because if Z is random, then G to the Z times H to the minus E is also random. So this is a random value in the group, which has exactly the same distribution as choosing A to be G to the R for a random R. But also G to the Z equals A times H to the E trivially, because that's the way I chose them. Look, A equals G to the Z times H to the minus E, so G to the Z equals A times H to the E. So I can easily cheat. If I know ahead of time the E, it's just trivial to simulate. I just compute this equation, which is trivial, and then I've simulated. But it's not very satisfactory because, when we have semi-honest adversaries, we don't need them to prove anything, right? We saw in Yao yesterday, I don't need to ask a semi-honest party to prove in zero knowledge that it did the correct thing, because I know that it did the correct thing. So it's sort of like, what is honest verifier zero knowledge even interesting for? I don't need it for semi-honest adversaries, and as soon as the adversary is malicious, it doesn't help me because it's not zero knowledge anymore. The good news is that it's actually enough to yield very, very efficient zero knowledge. And that's going to be the main point that I'm going to try and get across, that Sigma protocols are a great tool to get highly efficient zero knowledge. And in fact, I'm going to get zero knowledge by paying almost nothing. I'm not going to repeat 40 times and make E be very small, a single bit. I'm going to add something like 3 exponentiations, and I'm going to have provably a zero knowledge proof. Not just honest verified zero knowledge, but general zero knowledge. So it means I can do this at almost no cost. Okay. So first let's go into more a bit what a Sigma protocol is in general. I have a template which is as follows. We have a prover and a verifier as beforehand. The prover has some witness. And then the template is simple. The prover sends a message A, some message. The verifier always sends a random T-bit string E. This is what's called a public coin proof system. And T is going to be a parameter which will tell me what my error will be. My error, my soundness error will always be 2 to the power of minus T. And then the prover will send a reply Z. And the verifier will accept based only on the public transcript. There's nothing secret about what the verifier did in order to generate E. It's just a random value, and everyone can verify just based on A, E, Z, and X. This is actually important for what Benny was talking about yesterday. When I'm doing GMW, it's very useful to have the proof be something that in the multi-party setting that everybody can verify if it's okay or not, and this is exactly a transcript like that. Completeness of the same thing. I'm going to know how you define a Sigma protocol, because a Sigma protocol is not zero knowledge. It's something which is much more restricted. I'll be able to use it to get zero knowledge. The good news also is that, how many of you have tried to prove that something is zero knowledge in the past? Okay. Then you know it's a bit annoying, because you have to generate distributions and you have to consider these verifiers that are bought. And it's work, and when it's work and it's difficult work. How many of you tried to prove that something is a proof of knowledge? That's even worse. Okay, that's even harder. It's significantly harder than proving that something is zero knowledge. The good thing about a Sigma protocol, I'm going to define something very, very simple. It's very, very easy to prove that it's a Sigma protocol. Really, it's much, much simpler to prove that it's a Sigma protocol than a zero knowledge or zero knowledge proof of knowledge. And then I'll give you an automatic transformation to get a zero knowledge proof of knowledge. So not only am I giving you something which is efficient for use, it's also efficient for research, because you don't have to spend the time proving that it's a zero knowledge proof of knowledge. So the first requirement beyond completeness is what's called special soundness, and this is like the proof of knowledge property, but again, it's not strictly a proof of knowledge by that definition. That's why it's called special soundness. And what it means is there exists an algorithm A that, given any X, any statement, and given any pair of transcripts, A, E, Z, and A, E prime, Z prime, where E does not equal E prime, that machine will output a witness. Okay, so in contrast to a proof of knowledge where the extractor interacts with the prover and has to extract with the same probability that the prover extracts, here it's a very, very simple, clear requirement. I have 2 sets of transcripts with the same first message. They differ in the second message. then I can obtain the witness. Right? So just a simple algebraic check that I can actually do this. There's no distributions, there's no probability of accepting, nothing. That's a very, very easy, clean requirement. The second thing is something called special honest verifier zero knowledge. It's called special because honest verifier zero knowledge would say generate the same distribution, but here I'm actually going to give you E itself. I'm going to say I'm going to set X and E for you. Giving you X and E, I want you to generate a transcript AEZ that has exactly the same distribution as a real execution where V sends E. So what's special here is that I'm actually forcing you to work with a fixed E. And you don't need this for every transformation on Sigma protocols, but for some transformations it's needed. And I don't know of any Sigma protocol where you don't have this anyway. So you're given X and E, and you manage to generate A and Z. Note that in a discrete log, that's exactly what we did. We chose a random Z and E, so we wouldn't have any problem being given E, then choosing a random Z, and then on the basis of that choosing A. Okay, and notice, by the way, this is perfect. Okay, I want the distribution to be exactly the same. You could develop a theory of Sigma protocols which is computational as well, but we have to see whether all of the transformations go through. For now, anyway, this is going to be a perfect simulation. Let's take another example. Okay, so we've seen now, I hope that it's clear to everybody why Schnorr's discrete log protocol fulfills this. Completeness is obvious, special soundness we showed directly, and this also we showed. So all of those we showed on Schnorr's protocol. If there are any questions, please ask, by the way. We started asking yesterday, but sort of questions waned out. You feel free to ask at any time. Schnorr's protocol is only interesting as a proof of knowledge because the statement is trivially always going to be true. What about Diffie-Hellman tuple? Okay, so I'm given G, H, U, and V, and I'd like to know whether there exists a W so that U is equal to the G to the power of W and V is equal to H to the power of W. In other words, this is a Diffie-Hellman tuple. Okay? This is actually very useful in many protocols, and we'll see it later on this afternoon. I'll use such things a few times. I think Benny will also use this in the next talk. Note that this is not necessarily always going to be true. So this is already a statement that may or may not be true. And notice also that if W is random, then you can't tell by looking at the tuple GHUV whether it is a Diffie-Hellman tuple or it's not a Diffie-Hellman tuple, as long as the decisional Diffie-Hellman assumption holds. So the decisional Diffie-Hellman assumption says that GHUV of this form is indistinguishable from GHUV of the form where they're all just where U and V are just random values. So the protocol is as follows, and it looks very, very much like Schnorr, but just doubled up. So P chooses a random R and computes A equals G to the R and B equals H to the R and sends A and B to the verifier. The verifier sends a random E, and the proof it just answers Z equals R plus EW mod Q. So this is exactly the same as Schnorr, but instead of doing it on one, I'm doing it on both. The idea intuitively, and the verifier checks that G to the Z is A times U to the E, and H to the Z is B times V to the E. The idea is that essentially what we've done here is made two discrete log protocols at the same time, two discrete log proofs at the same time, but by sending only a single Z and a single E, this means that there has to be the same relation between U and V. They have to have the same discrete log or else this thing's not going to work. That's the intuition, we'll prove it in a second. Yeah?
How do you choose G and H?
G and H, that's completely orthogonal to the discussion here. It doesn't really matter. Think of them as being arbitrary generators. Usually G will be the generator and H will be a random value as well. But
if H happens also to be a generator, then the answer is positive.
H should be a generator. In general, when you do this, H should definitely be a generator, and the answer is not always. It's not always positive. If H is not a generator, then this is not a Diffie-Hellman tuple. Okay. So that's our proof again on the side, so you can see what's going on. Completeness is exactly as in discrete log, it's obviously going to hold. What about special soundness? Again, here I'm given two transcripts with the same first message and different continuations, and I want to show you that I can extract the discrete log. Okay, that's what I want to show you. And again, I don't need to prove anything about distributions, just this clean statement. So let's look here. Because of that, because we have these two statements, then we know that both of them are accepting these two transcripts. That means g to the z equals a to the ue, g to the z prime equals a to the ue prime, h to the z is b to the ve, and h to the z prime is equal to b ve prime, because these are the two checks that we're doing here, and the checks all pass in both of the executions. And therefore, exactly like in the discrete log, we have the w equals z minus z prime divided by e minus e prime. Exactly like in the discrete log setting. The only difference here is that I get it twice. I get it twice, both on u and both on v, but I get the same value. I have to get the same value, which is z minus z prime, e minus e prime. So if both checks pass, then I can easily get the discrete log. Okay, is that clear? What about special honest verifier zero knowledge? I'm given now E and the statement, and I want to generate something which is distributed exactly like a real proof. Again, I just choose a random Z, and Z indeed is random in a real execution. It's R plus EW, R is random. And I compute A and B to be exactly what I want it to be. I want the check. The easy way to do this, by the way, is just look at what the check is and then just to reverse the order of things. So I want g to the z to equal a to the, times u to the e, so I just choose a to be g to the z times u to the minus e. This is all efficiently computable because I know the order of the group, so I can easily compute also inverses. And I choose b to be h to the z times v to the minus e, and again that means that the check will pass at h to the z equals b times v to the e. So this has exactly the same distribution as a real proof. Okay, and this is really the complexity of proving that something is a sigma protocol. Okay, it's really, really easy. If you want to write it in full with all the details, it's even me who writes really, really long, it's going to be hard to go over half a page. It's really short. Okay, so what are basic properties of sigma protocols? Any sigma protocol is interactive proof with soundness error 2 to the minus t. It's easy to prove, it's based on what we said. Also, properties of sigma protocols are invariant under parallel composition. So if I run many sigma protocols together, then in parallel, the result is a sigma protocol as well. Why is that important to me? Because I have automatic transformations that work on sigma protocols. I know how to take a sigma protocol and transfer it to zero knowledge. So let's say I want to prove 20 things in parallel in zero knowledge. The old way of doing things is to construct 20 zero knowledge protocols that are all composed in parallel, which itself is very non-trivial to prove, by the way. To prove that zero knowledge protocols composed in parallel is non-trivial. See a paper by Oded in 2003, I think, that shows that the Goldreich-Kahan protocol composed in parallel. It's very, very complex. And then use them. This way of working is completely different. It says, take 20 different sigma protocols, put them in parallel. It's now a single sigma protocol, which is the compound of 20 different statements. I'll show in a second exactly how that works. And now apply the transformation once to get a zero knowledge proof of knowledge. Again, it's much, much easier. In addition, any sigma protocol is a proof of knowledge by the classic definitions of proofs of knowledge, again with this error of 2 to the minus t. So this more complex claim that you have an extractor that can obtain the witness with approximately the same probability that the prover can convince the verifier all holds just from the special soundness property. What tools do I have for sigma protocols that make it so attractive? I can easily prove compound statements like the AND of a number of statements, the OR of a number of statements, and even the subset of a number of statements. I have now 20 statements. I want to prove to you that 10 of those are correct. You may think, sounds interesting, but why is that useful? Wait for this afternoon. It's very, very useful. I can easily get zero knowledge from sigma protocols. I can easily get zero knowledge proofs of knowledge from sigma protocols. And there are actually many other things that if we have time at the end of the talk, I'll show how you can construct commitments and trapdoor commitments from sigma protocols, how you can construct hash functions from sigma protocols, but they're sort of not that connected to CQ computation. Okay, so let's go into some of these tools. Proving AND of sigma protocols. Okay, I want to prove to you that this tuple is Diffie-Hellman tuple, and this tuple is Diffie-Hellman tuple, and this statement this statement is true, and a whole lot of different statements. I want to prove to you that they're all true. For example, I want to prove to you that the Yao circuit that I constructed is true. One way of doing that is by proving an AND that every gate that I constructed is correct. Okay, and that is actually a protocol which works in that way. And that's the AND of many, many statements. So how do I do that for a sigma protocol? Just run them all in parallel and use the same E in all of them. You don't have to use the same E in all of them. You can use a different E, but it suffices to use the same E, so you may as well. So the prover sends all of the first messages, the verifier sends a single E, and the prover answers all of the messages based on that single E. Why is it okay to use a single E? It seems strange. Doesn't that degrade security? If I was thinking about zero knowledge, I would be suspicious. But for sigma protocols, it's much easier to see. Do you want to tell me why?
Every first message is random. Then they are not linked.
But it's more than that. So the first message may be random, but maybe I'm introducing dependence based on E. Why does soundness hold? Why can't I cheat with a higher probability? You almost said it. What does the soundness property of sigma protocols say? You can't, right, for a single A, you cannot answer, if the statement is not correct, you cannot answer two different E's. As soon as the statement is correct, you cannot answer with two different E's, because as soon as you can, you're able to extract a witness. If a statement is not correct, you definitely can't get a witness. What's more important is the special soundness requirement doesn't say anything about the distribution over E. No one says you have to use a random E. Okay? In fact, there's no need to use a random E. It's enough for me to have high enough unpredictability, high enough entropy, that the prover can't guess ahead of time what my E is with probability greater than whatever my soundness value is that I want. So I don't need independent E's, I don't need random E's. As soon as I can send the same E for all of them, in every single execution, there's only one E that the prover can answer, and that means that the error is going to be e to the minus t exactly as I want. I do want to comment that sometimes you can actually do better than this. It's possible to batch sigma protocols. For discrete log, you can actually batch incredibly efficiently. You can run thousands of discrete log protocols at the cost of almost one. But even for the Diffie-Hellman one, you can actually do this in about a quarter of the time. By even less than a quarter of the time, sorry. What you can actually do is take a whole lot of Diffie-Hellman tuples, generate in a special way one Diffie-Hellman tuple, and prove a single sigma protocol for all of those statements. So sometimes you can do better than just running in parallel. Even though this isn't that much cost, it's still, you can sometimes do even better. It's worthwhile looking at that if you need to prove many statements at once. How do I do an OR of two sigma protocols? This is much, much more complicated. Why do you think it's much, what's the intuition why it's much more complicated? It's written here, so it's not that difficult. The problem with the OR is that you want the zero knowledge property. It means that it can't reveal which statement you know and which you don't know, or which is correct and which is incorrect. So I have two statements, one of which is correct and one of which is not correct. It seems very, very difficult for me to prove that I know one, or that one is correct, without revealing which one I know. The classic way of doing this, in the general zero knowledge theory way, is doing what? Taking the compound statement, doing a car production from the compound statement. That's obviously not going to be efficient at all. With sigma protocols, and this is really one of the most beautiful constructions, we can actually do this really efficiently and elegantly. This is an ingenious idea from CDS, which is Kramer, Damgaard, and Schoenmakers, right? Yeah. The idea is as follows. If E is known ahead of time, then the simulator is able to, then we can cheat, right? If I know the challenge ahead of time, then I'm able to cheat. The only time, because I can use the simulator to generate a transcript. If I don't know E ahead of time, then obviously I can't cheat. So what I now am going to do is construct a protocol which enables me to cheat in exactly one of the executions by using the simulator. So actually what's interesting is that if you want to actually use this construct, you actually have to implement the simulator for Sigma protocol. So simulators now become actually something that you run, not just something that you use in a theorem to prove security. You're actually going to run the simulator. How's it going to work? So I want to prove that either x0 is correct or x1 is correct. And P is going to send the first two messages, A0, A1, for each of these two statements. However, what will be interesting is how the prover constructs those messages. The verifier will send a single challenge E, and the prover will reply with two challenges, E0 and E1, whose XOR equals E, and two final messages, Z0, Z1. I didn't say how the prover constructs A0 and A1, but I want you to think about what the meaning behind this is. The prover is able to essentially choose any E0, E1 that it wants, but under a specific constraint. That constraint is that they XOR to the random challenge sent by the verifier. And then the prover just answers Z0, Z1 based on those E0, E1. Now what this means, so V accepts if E0 XOR E1 equals E, and also both transcripts are accepting. So how does this actually work? How can I use this to my benefit? My claim is as follows. Let's say I don't know, or let's say that X0 is not correct. If X0 is not correct, then for every A0 that I send, for how many E's can I answer? How many challenges can I answer? 1. So that completely binds E0. Whatever A0 I sent, there's only one E0 that I can answer for, because the statement's not correct. So I'm now completely bound to E0. Now if I have to choose E0 XOR and E1 so they XOR to E, E0 is fixed. E is also fixed because the verifier chose it, right? That means I have no choice over E1. So E1, essentially E, because E0 is completely bound, a random E gives you a random E1. And that means that I must be able to prove the statement for X1. Let's see it on the next slide. P sends two first messages, A0, A1. Okay, so that's reversed on the slide than what I said. P has a witness for X0 but not for X1. Okay, so P knows X0, it doesn't know X1, or X0 is correct and X1 is not correct, it's the same thing. So what P does, P doesn't know how to prove for X1. But what the prover can do is run the simulator. So the prover can choose a random E1 and generate a transcript A1, E1, Z1. On the other hand, for A0, what does the prover do? So, run the real proving protocol. The prover knows a witness for X0. So it just generates A0 using the general protocol. And now it sends A0 and A1. The verifier sends a single challenge, and the prover now has no choice but to use E1, the E1 that it gave to the simulator in order to send Z1. It cannot answer for any other E1. But that's fine, because the prover can answer for any E0, because the prover knows the witness for the first statement. So therefore the prover computes E0 to be E XOR E1, which are already fixed, sends E0 and E1 to the verifier and answers with Z0 and Z1. Notice that Z1 is exactly the same as the one here, whereas Z0 is computed using the witness. So this is something you can clearly do. It's a little bit strange the first time because I'm actually running a simulator in a protocol. It's not just something to use in a proof, but this all clearly goes through and completeness clearly holds. The prover can easily do this, has no problem obtaining A0 and A1 in this way, and then answering for every E, answering correctly. What about soundness? Why does soundness hold? So, what we said is that P doesn't know a witness for X1. So, as we said, this means that it can only answer for a single E1. That means that for every E that the verifier sends, there is a different E0 that the prover has to answer for. Okay, every different E defines a different E0. Now, if the prover wasn't able to answer also for, or let's say different, not in that way, in a positive way, therefore if the prover can answer for two different E's, we must be able to get two different transcripts relative to the same A0. Because E1 has to remain fixed. Or in general, if E1, it doesn't remain fixed, and the prover had to know also E1. So for every E, you can only fix one of the E0 E1s, the other one has to differ for different E's. So if I have two transcripts with different with E and E prime, that means I have to get two transcripts with a different E0 E0 prime or E1 E1 prime, and then I'm able to extract the witness. Okay, so that's exactly what I said here. Relative to the first message A0 A1 and two different E's, E prime, at least one of E0 and E1 have to be different to E0 prime and E1 prime. Otherwise, E has to equal E prime. And that means that I'm going to obtain two different continuations for the same first message in at least one of the executions, and I'm going to be able to extract the witness. Is that clear to everybody? Because it's very important, because the next step is going to be significantly complicate this construction. So if it's not clear, please ask. If you're not overwhelmed by its beauty, then that's also a problem. It's really nice. And for honest verified zero knowledge, well, that's easy because I can choose both E0 and E1, and so it's not a problem now. I just run the simulator in both cases, and by the perfect zero knowledge property of each one, it's fine. Okay, so just want to note that this OR doesn't have to be the same language even. And that's because we required for our template that in a Sigma protocol, E is always just a T-bit string. So all of the Sigma protocols have this same format of the verifier query, so I can actually do the OR of any different number of statements that I want. I can do the AND as well. I can basically make an arbitrary compound statement based on ANDs and ORs and compile it all into a single Sigma protocol using this method. The problem is that if I start doing many, many ORs, and I can only know how to do two at a time, it's going to start getting expensive. If I wanted to do either all of these are correct or all of these are correct, and that's fine. I construct a Sigma protocol based on ANDs, a single Sigma protocol. I construct another single Sigma protocol, which is the AND of many statements, and then I OR them together using this method. But what if I want to say that x0 is correct, or x1 is correct, or x2 is correct? Then you...
Why doesn't the same thing work?
It works, but what you have to do is you construct one Sigma protocol to show that x0 or x1 is correct.
No, but why can't you use three? And you have to have the XOR of the three values, so you still can choose only one.
If it's just 1 out of 3, if it's 1 out of 3, it's fine. You're right. If I want to do the OR, which is just 1 out of 3 or 1 out of 100, that's fine. To do 1 out of 100, so what if I want to do that 2 out of 3 are correct? That's going to be more of a problem. But if it's 1 out of many, then that's fine. You're right. So what I want to do is actually want to prove something much more complicated. I want to prove that k out of n statements x1 through xn are correct. Because if it's 1 out of n, that's a very important comment by Iran. If it's 1 out of n, that's not a problem. I can use exactly the same method that I use now. But if I want to prove k out of n, this is very, very difficult. Or at least it doesn't seem to follow from the previous way. So let's denote by A the set of indices that the prover knows, and by the other ones to be B. What I do, I'm going to go through this relatively quickly, give you the general idea, and afterwards you can read it. I'm going to use secret sharing with threshold n minus k. And I'm going to, just to be concrete, I'm going to use Shamir secret sharing, although that's not necessarily the best way to do it, with field elements alpha 1 through alpha n, and a polynomial f, again of degree n minus k, and it's going to have some free coefficient which I'll denote to be s. And based on this secret sharing scheme, the share of s for party pi is going to be f of alpha I. Okay, so this is what Benny talked about yesterday. Now what the prover is going to do is it's going to generate, for every I in B, means the statements that it doesn't know how to prove, it'll generate AI, EI, and ZI using the simulator. But for every A that it does know the statement, it will run it as in the protocol. So far, exactly the same as beforehand. Okay? The ones that I know, I generate correctly. The ones that I don't know, I use the simulator. Excuse me, please. The prover then sends A1 through AN to the verifier. And the verifier now sends a random field element E. And what the prover does is it finds a polynomial f of degree n minus k that passes through all the points alpha I, ei, and 0e. Okay, ei are the points that are generated using, for I and B. It means the ei's are the ones that the prover chose using the simulator. These are the ones that are fixed for it. So essentially, if you think about it, this over here, by sending all of these AIs, the prover sent n minus k AIs for which it doesn't know the answer. Okay, it's only able to answer for a specific EI. What that means is the prover fixed n minus k points of the polynomial. Now, a polynomial of degree n minus k, how many points completely determine the polynomial? N minus k plus 1. The verifier sends a random E, and that completely determines the polynomial. So the prover has n minus k points that it fixes, and the verifier comes and gives it an additional random point, and that completely fixes the polynomial. Once the polynomial is completely fixed, the values ej, which are equal to f of alpha j, for every j and a, are now fully determined. Okay? So by the verifier sending E, it essentially implicitly fixes all of the values ej for j in A, the ones which the prover knows how to prove. But what's important is the prover has no freedom here, because the prover is bound to the n minus k statements for which it doesn't know how to prove. It doesn't have any freedom there. So n minus k points are fixed. There's one degree of freedom. The one degree of freedom is now completely fixed by the verifier, and that means that all the other KEs are fully determined for the prover, and it has no control over them. So the prover, fortunately for those J's in A for which it knows the witness, it's able to actually compute the answer for every E. That's by the completeness requirements. So in particular, the E's that are determined by the polynomial, it's able to compute and then send the answers back. It sends Z1 through Zn. The Z's for which it knows the answer are the ones that computed correctly, and the other ones using the simulator. The soundness follows because the number of possible vectors which are obtained, or values for all the ones which the prover knows, the k which it knows, there are exactly the number of possible vectors are exactly equal to the size of the field. So if the field is large enough, the prover will only be able to reply, or the prover will only be able to cheat with probably 1 over the size of the field. Okay, this is a little bit subtle, but I encourage you to look at the paper. You can also see that, in fact, it's not just there are f possible vectors. The vectors also have to traverse all possible values, because that is derived from the secret sharing property. Otherwise, I would know that some values are not possible, and that would limit the possibility of what the free coefficient is, and so on and so forth. Okay, so that's the general construction. As I said, this is very useful, and it's also very, very efficient. Notice that the cost here is 1 sigma protocol for each statement, and running a very simple Shamir secret sharing. In fact, in CDS, they even have, if k is less than n over 2, they have an even more efficient way of doing this using matrix multiplication. So this is just, I can get the OR of k out of n statements at the cost of running a single sigma protocol for every statement, which is just amazingly cheap. Yeah.
Does the verifier have to reconstruct the alphas to check the proof?
Yeah. The verifier has to check that all of the EIs that it receives, the prover, what the prover will send is all the EIs together with all the ZIs. And what
the alpha is?
Oh, the alpha I's are fixed.
Oh.
The alpha I's are known. This is like in a secret sharing scheme when you know the points of what the points are that it's supposed to go through. So alpha 1 through alpha n are fixed, And what the prover does is sends all the E's and the Z's, and the verifier checks that, interpolates all of the E's, checks that they're on the same polynomial, they're all on a single polynomial of degree n minus k, and that their free coefficient is E, which is the value that it sent.
So I pre-specify for each statement the alpha.
Exactly, yeah.
Okay.
Yeah. This is a fixed parameter beforehand, yeah. And it does involve interpolation by the verifier, but this is not something which is so expensive, unless you have hundreds of thousands. Okay, in fact, this can be generalized to any monotone formula. So you can use this type of scheme to prove any monotone formula, which is basically a formula of ands and ors in any way, set up in any way, and that gives you really huge freedom in proving compound statements. Okay? This is really an amazing thing. Okay, what about zero knowledge? I promised you that you'd actually get zero knowledge, and that it's not Sigma protocols within themselves. We saw that they're very nice. We can do really nice things with compound statements, and it's really easy to prove that something's a Sigma protocol. But bottom line, I want zero knowledge, and I want zero knowledge proofs of knowledge. So how do I get zero knowledge? And the basic idea is very, very simple. Just like in regular zero knowledge or zero knowledge for all MP that we've seen, I just want the verifier to first commit to its challenge E before the prover sends the value A. And the verifier does this using a perfectly hiding commitment. So basically the protocol is as follows. Perfectly hiding commitments can generally take 2 rounds, or at least 2 rounds. So the prover sends the first message of the commitment protocol. The verifier then sends a commitment to its query E based on the first message from the prover. The prover then sends A. The verifier decommits by sending E and R. It sends both E and R because the prover will want to check that indeed that was the committed value. So the prover checks that indeed the commitment value got here equals the commitment to E using randomness R. And then, if yes, it sends a reply Z. And then V accepts based on X, A, E, and Z. Why does this help me to get zero knowledge, anybody? How will the simulator work? How can it cheat? The simulator can cheat. How? The simulator runs the verifier. It receives the commitment value, sends A. How does it send A? It doesn't know the witness, so how does it send A? It uses the simulator using any arbitrary E. The point is, because the simulation is perfect, A is actually independent of E. In a real protocol execution, the prover sends A independently of E. So, when I say that a Sigma protocol, the simulation is perfect for honest verified zero knowledge, it means that A is actually independent of E. The simulator can just choose a random E and send the first message A, and the verifier then either commits or doesn't, either decommits or doesn't decommit. What do I do if the verifier doesn't decommit? Either I'm hard of hearing or people are whispering. You just abort. Right? So if the verifier doesn't decommit, then I just abort, because in a real execution with that probability, the verifier didn't decommit. So I told him just to get lost because it didn't want to do it. So I don't want to work with it either. And if it does decommit, I now know E. If I now know E, what can I do? Rewind. Where do I rewind to? I rewind to this point. Obviously, I keep the same commitment C. I now rewind. Okay, this is like on a game show where you have to choose the right curtain, but you're given the chance after you finish the show when you see the curtain to rewind the host and now choose the correct curtain. So now I know the value E, and I can send the message A based on E. Do you remember that I said that I actually want this stronger property that the simulator for the honest verified zero knowledge is given a specific E and then generates? This is for one example of where I actually need that. Because now I have E given by the verifier, and I can now construct a simulation, AEZ, which looks exactly like a real execution based on E. The prover sends that new message A. The verifier either decommits or doesn't decommit. If the verifier decommits, what do I do? if it does decommit? I'm very hard of hearing today. What do I do if the verify does decommit? I send Z and I've finished. What happens if the verify doesn't decommit? What do I do if the verify doesn't decommit? I'm in trouble. I have to get I have to finish the execution because the first time the verify did decommit. So what do I do if the verify doesn't decommit? Rewind and try again. Rewind and try again, and again and again and again and again until it succeeds. What's the good news? What's the probability that it's going to succeed? In every execution, exactly the same. So it's an expected polynomial time simulation. The probability that it decommits in any round is P. So the expected number of tries I need is 1 over P. P times 1 over P is 1. We're all happy. Okay? So let's go through it here. The soundness follows from the fact that it's a perfectly hiding commitment. If it's a perfectly hiding commitment, it means that nothing whatsoever is revealed about E from the commitment value, and so everything follows as beforehand. Zero knowledge, we actually did this already, so I'll just go through it there. And the analysis is simply that the probability that I succeed in any one is exactly P. I need to try 1 over P times some expected polynomial time, and in terms of succeeding, eventually I'll have to succeed because I just continue until I succeed. Okay, questions? But the good news is you never actually have to prove this. Right? That's the good news. The good news, this has been done once for you. All you have to do is prove this is a Sigma protocol. Okay, so now I have a question. If computational soundness suffices, okay, so it's enough for me to use to get an argument. I only need to preserve security in the presence of a polynomial time prover. Then can I use a computationally hiding commitment scheme? Firstly, why would I want to? Why would I prefer to use a computationally hiding commitment scheme rather than a perfectly hiding commitment scheme?
More efficient.
It's more efficient. It's only one round, for example. I can do it non-interactively. I can do it using more simple symmetric techniques based only on one-way functions. But is it enough? No one's willing to gamble? Okay, who says it's enough? Raise your hand. Who says it's not enough? Raise your hand. Who abstains? So it seems like we have a thing here. You can vote, but it doesn't seem to work. I think it does work. You just know how to turn it on. Maybe then we get more people raising their hand because you can vote anonymously. Or we could build a protocol for voting, but that might take too long. So actually, I think that it should be enough. It doesn't really help me because you're right, it's not enough. And the reason why it's not enough is very, very technical. It's only when you start writing down the proof do you realize why it's not enough. And the reason is you try to construct a reduction. What you basically want to show is that if the prover can cheat, then I can break the commitment protocol, the commitment scheme, right? That's anything computational needs a reduction. That's the problem with computational cryptography. You actually need to do reductions all the time and you get tired. So what I need to show is that if there exists a prover that can prove an incorrect statement, then I can distinguish commitments to one random value to commitments to another random value. So how would I do that? I receive a random commitment externally, and I see if the prover is able to somehow successfully prove an incorrect statement. The problem is the reduction just completely falls apart, because how do I know if the prover has succeeded in convincing me, proving an incorrect statement? How do I know? After I finish the execution. But as part of the execution, what do I have to do? Decommit. When I'm running a commitment reduction, I can't decommit. I'm given a commitment externally, and I want to see if the prover can convince me based on that commitment, but I can't do that because I have to decommit. So basically the reduction completely falls apart and you die. You could send a commitment and then prove in zero knowledge that it's a certain value, but that would already be much more expensive than using a perfectly hiding commitment. So there's no point. But are perfectly hiding commitments anything to be afraid of? I argue not. There are Pedersen commitments, which many of you might have seen, which basically mean that you can do this in two exponentiations. In a regular discrete log group, do an elliptic curve group, and it's just a few milliseconds. So we have a generator G in a group of order Q. The commitment protocol is very simple. The receiver chooses a random Z and sends H equals, I guess it chooses a random K, because otherwise there isn't any connection. So the receiver chooses a random K and sends H equals G to the K. And then the sender will send, this is the first message of the commitment protocol, and the sender will send the commitment, which will be G to the R times H to the X, that's a commitment to X, for a random R. Why is this hiding? Well, for every X and Y, there exists R and S, so that R plus KX equals S plus KY mod Q. Now notice that this is R plus KX. Now there exists also an S and a Y, so that C will equal G to the S times H to the Y, because that's what's over here. So there always exists an S and Y for every R and X. And that means that a commitment to X looks exactly like a commitment to Y. It just depends whether I use randomness R or use randomness S. Now this begs the question as to why is it binding? Why is it binding? I mean, if you can always find an S and a Y, then I can decommit to anything that I want. So the answer is that it always exists. It doesn't mean that I can always find it efficiently. And indeed, if I can find X and R and Y and S, so that G to the R times H to the X equals G to the S times H to the Y. In other words, I sent the commitment value here, and I managed to open it in two different ways. I sent some value C, and now I'm able to open it to both X and Y, and as I can send both XR and YS, then that means, using exactly the same thing we did in Schnorr, that K equals R minus S divided by Y minus X. Okay, that's just, look, G to the R minus S equals H to the Y minus X. So H is G to the R minus S divided by Y minus X. And that means that if I have two openings, I can find the discrete log of H. But H was chosen at random by the receiver for the commitment, so the sender cannot know that value. So it's computationally binding and perfectly hiding, and very, 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 very cheap. Committing costs three exponentiations, one by the receiver and two by the sender, although if you're doing many, many commitments in a protocol, that first message is only done once, so you can amortize it out. And decommitment is just rechecking, so it's another two exponentiations. This is really, really cheap. So we get overall that using Pedersen commitments, the transformation from a sigma protocol, if you're happy to rely on the discrete log assumption, it's not even DDH, it's the discrete log assumption, which is great. Using Pedersen commitments, the transformation from a sigma protocol to a zero knowledge protocol costs 5 exponentiations in any group in which the discrete log problem is hard. So this doesn't cost. This is really free. And remember, if you're doing compound statements and you're proving 100 statements, you first construct a single sigma protocol. And then you apply this. So I can prove 100 statements in zero knowledge. This additional overhead of 5 exponentiations I pay once for the entire 100. This is really cheap. What about a proof of knowledge? What?
I'll buy it.
You buy it? Good. The software is expensive though. So is the previous protocol a proof of knowledge? Because often we don't always need proofs of knowledge. Sometimes zero knowledge proofs are enough, but often in secure computation we also need proofs of knowledge. For example, in GMW we need zero knowledge proofs of knowledge for the commitment input, for the input commitment stage, and later on to prove that we acted correctly, we just need regular zero knowledge proofs. But we also want to have a transformation for this, and it seems not to be. Why does it seem not to be? Remember, the extractor for the sigma protocol has to obtain two two extensions of the same transcript. So it has to have the same first message A and obtain an extension with E and E prime. The problem is that the prover may choose its first message, a cheating prover may choose its first message A as a function of the commitment value it gets. What does that mean? For example, the prover applies a pseudorandom function to the commitment value in order to choose A. A cheating prover can always do that. Now what that means is if I want to change the value E as a simulator, I also can't break the Pedersen commitment. Because the prover sent me some G equals H, some H which is G to the K, I don't know what the discrete log is. So I have a problem. I'm unable to decommit to a different value, and therefore I'm bound to E just like a regular verifier. And if I rewind the prover many times, every time I rewind the prover, notice, just look at the proof for a second. Where is it? Where is it? This jumping around here. If you look at the proof, the verifier, the simulator will be committed here before it gets the message A. So if you want to rewind to get a different E, you have to go all the way back here. And now the prover may change its message A again. So this is the problem. And the solution, there are a number of solutions. One solution is to say, okay, so use a Pedersen commitment and have the prover prove a zero knowledge proof of knowledge that knows the discrete log of H. Then the have the verifier. It's a proof of knowledge. The prover sends this H for the Pedersen commitment. Now I'll have it prove in a zero knowledge proof of knowledge that it knows the discrete log. I'll extract the discrete log, and now I'm able to decommit to any value that I want. It works, but it's more expensive than I want, and I actually have a very, very cute solution to that. What I'm going to do is use a trapdoor, or what's called an equivocal commitment scheme. It means that if I know a certain trapdoor, I can decommit to any value. Now, Pedersen has this property. If I know the value k, if I know the discrete log of h, then indeed I can decommit to anything I want, because I committed by sending g to the r times h to the x, but I know k. If I know k, then I can easily find S so that r plus kx equals s plus ky mod q for any y that I want. Just compute s to be r plus k times x minus y mod q. So if I knew k, then I could easily decommit to any value that I want. The problem is I don't know k. So here's the idea. The verifier will use its there's a word missing here. Have V first commit to its challenge E using a perfectly hiding trapdoor commitment. So now it's not a regular perfectly hiding commitment, one that has this trapdoor. The prover will send alpha, which is the first message. The verifier will send the commitment. The prover will send A. The verifier will send E and R, proving that it decommitted correctly. So far I haven't done anything differently. It's exactly the same as last time. The prover will check that the commitment is correct. And if yes, it sends the trapdoor and the final answer Z. It looks very weird. I mean, I'm just playing a stupid game. Why? And if the prover doesn't send the trapdoor, so I won't accept the proof? No, I won't accept the proof, because a valid proof also has to have a valid trapdoor. The verifier will accept if the trapdoor is correct, so I need the scheme to have a property that I can verify the correctness of the trapdoor, but that's easy. So if the trapdoor is correct and the statement is accepting. So all I've added is one step, which is to send the trapdoor. Let's see the resulting protocol. This is if I'm using Pedersen. It's exactly the same as beforehand. The only difference is that I'm sending k here and also verifying that indeed this is the correct trapdoor. Does anybody see now why I've solved the entire problem and this is a proof of knowledge? It's a proof of knowledge. I verify the proof once from the prover. Once I verify the proof once from the prover, if the prover didn't convince me, then in a proof of knowledge I don't have to do anything. But if it did convince me, then what do I have in my hands? I have the trapdoor, I have k. I can now rewind only back to here. I don't have to rewind beyond this. I can rewind to here and now give a different E, because now I can decommit to anything that I want. And what's the cost? Well, we've said that. 6 exponentiations. I added 1 exponentiation to the entire protocol, and now I have a zero knowledge proof of knowledge. You should be saying, and the best part of all, it's already been proven. You don't have to do anything. Just build the Sigma protocol and then use this. Okay. Okay. So just to sum up a little bit, I'm out of time. No. Yeah. We started a few minutes late, so I'll go a few minutes later. Worst comes to worst, we won't have lunch today. There are some people who are actually amused by that. Now, we typically want zero knowledge, so why am I dealing with Sigma protocols? I've said this a few times, I want to make it very clear. We have many useful general transformations that we've seen, the parallel composition, compound statements, and these zero knowledge and zero knowledge proof of knowledge transformations, and it's much, much easier to work with. And I really think that when we have these tools that help us to prove our proofs in a much simpler way, it's best for everybody. There's less chance of making mistakes, and also we save man time, so why not? I want to give some examples before we finish of where these very simple discrete log and Diffie-Hellman tuple type proofs actually show that they're actually something much, much more general. So let's say I want to prove that an El-Gamal encryption under some public key is actually to a value m, but I don't want to actually decrypt. Well, it's actually very simple because by El-Gamal encryption, if it's an encryption, U and V is an encryption to M, it means that U equals G to the R and V equals H to the R times M. But that means that G, H, U and V divided by M is just a Diffie-Hellman tuple. So if I want to tell you, here's a ciphertext and this is an encryption to M, but I don't want to actually decrypt it for you, and there's a reason why I want to do these things, I'll show you in a minute, then I can do this very, very simply by just proving that it's a Diffie-Hellman tuple. So that's what we've already seen. Okay. What about efficient coin tossing? So the way to do constant round coin tossing that I know for a long string at once is as follows. I choose a random X and I send an encryption to that X, and then I prove that I know the encrypted value. To prove that you know the encrypted value without telling you what it is, it's just enough actually to prove that I know the discrete log of H. So that's an easy proof. I've already shown how to do that using a Sigma protocol. The P2 then chooses a random Y, and P1 sends X, but without opening, without decrypting or decommitting. But just proves that the encrypted value is actually X. Well, I just showed you already that that's the same as proving that it's a Diffie-Hellman tuple when I divide it by X. And then both parties output X plus Y. Okay, so this is this goes back to a paper actually of mine from 2001 called Parallel Coin Tossing or something like that. And there it's written as a protocol with general commitments and general zero-knowledge proofs, and it looks like something which isn't going to be very, very efficient in practice. When you translate this to use El-Gamal and to use Sigma protocols, I didn't count, but it's probably like 20 exponentiations, and you've managed to toss a coin with full simulation and many coins at once, actually, a whole string, a whole field value with full simulation based in the presence of malicious adversaries. This is like the coin tossing that Benny mentioned yesterday for GMW. Using Sigma protocols, you can do this really, really efficiently, at least for the two-party case. Okay, one more minute. Pedersen commitment, I just want to show just so you can do. We saw what it was. What happens, I want to prove that I know the committed value. Okay, well, here's a special Sigma protocol for it. You can look in your slides. You can also, it's not expensive, you can prove also that you know a Pedersen value. What else can you do? You can prove that a Pedersen value, committed value is some X, similar to beforehand. This is actually just proving that you know the discrete log of something. So there are a few more examples. I just mentioned the highlights of a few things before I end. You can translate Sigma protocols into non-interactive zero knowledge in the random oracle model using Fiat Shamir, if you like the random oracle model. You can construct trapdoor commitments from any Sigma protocol. You know, we saw trapdoor commitments from Pedersen, but from any Sigma protocol you can actually construct. You can construct hash functions, and you can also do other things, but you can see in your slides. So don't be afraid of zero knowledge. Using zero protocols, it's easy to work with and it's very efficient. And that's it. I won't prevent you from your coffee and cakes. So.